let me just mention one more thing before we go on to backprop, and this is an important thing as well. It's the difference between batch and incremental gradient descent. What we've talked about so far is batch gradient descent, which means that you look at all your examples, you compute your gradient, or same thing. The same thing is going to apply when we do backprop, right? You compute your gradient and then you update by that gradient. Okay. This is actually right, the algorithm that we had here. Let's look at it again, right? What happens is that I ran through all the examples, adding my deltas to the big delta, and then at the end of the day, I apply my big delta, which is a sum over all the examples, to the weights. Okay, and this is what our guarantees and our treatment is about. Okay, however, what people usually use in practice is incremental gradient descent. Let's see what incremental gradient descent is and why it might be better. Okay. And the difference is actually very, very simple, is that I don't wait until I've seen all the examples to update my weights. I just update the weights after each example. Right? You could speculate that this is a little bit like learning live versus learning in your sleep. Right? Presumably you're in reality, right? You're learning. The weights in your neurons are actually changing during the day. Okay? The analog of batch is, you store all of that up, and then at night you sleep, and then the weight learning happens. Maybe some of both is happening. In any case, this can actually work very well for learning. So number one, which one do you think is going to be faster, batch or incremental? Right, which one do you think is going to get to the optimum weights faster?
Batch, probably.
Batch, because?
Seems like you may be moving in wrong directions based on a few training examples.
So you're actually right about, so your justification is correct, but the answer is wrong. Hey, not bad, right? You get half credit, or maybe even more, right? So the problem that you just pointed to is a very real one, but let's hold off on it for just a second, right? Incremental gradient descent is usually a lot faster because you're doing many more updates. Right? Let's suppose that I have 100,000 examples. I have to go through those 100,000 examples before I even change the weights. Probably even after a few examples, it was already clear that I need to change the weights in this direction, so change it right away. This is why incremental often converges a lot faster, okay? Because it's just doing more updates, right? It's doing updates, n times faster, where, n is the number of examples. Nevertheless, you pointed to a very good example, which is, what happened to our guarantees, right? Are we guaranteed to converge to an optimum? We actually aren't anymore, right? Because now we're zigzagging. Now, there's a stochastic component to the movement of the weight vector, right? Before, the weight vector was just going straight to the goal. Now, the weight vector is jumping around. And this could be a problem. In fact, in learning a simple perceptron, it's usually never a problem. In learning a more complex thing, it could throw you off into a bad direction. However, this is where the second important thing comes in. Usually that noise part, instead of being hurtful, is actually helpful. Can anybody guess why the noise might be helpful? Right, you can see that the steps that we're taking are like the right steps with some noise added to it, right? You can look at it that way, right? So why would it be a good idea to add noise to the gradient direction? In the plain perceptron, that's not going to make a difference. But in backprop, it often improves things. Why might that be the case?
Avoid local optima sometimes.
Exactly, it helps me to avoid local optima, right? So suppose that I have something like this, right? And I want to get over here, but I'm converging towards here, right? But if I'm doing this with noise, it's like my rolling down the hill is bouncing, right? And if I let the ball bounce, I actually give myself some chances of getting over that little hump and into the right optimum. Okay? So the downside of incremental is that you have no guarantees anymore. So if you're of a theoretical mind, that may disturb you. However, if you're really of a theoretical mind, you'll try to come up with guarantees for that case, and people have, certainly. But on a practical level, it'll probably give you faster learning and a better result. So incremental is often the method of choice. Incremental is often also called stochastic, precisely because it's like having noise. Yeah.
Do you have to worry less about the learning rate in incremental? Because
you don't have to worry less, but you have to set it differently. right? It's the same trade-off as before, but obviously the ideal value of the learning rate for batch and for incremental are going to be different, right? For incremental, it's going to depend on the number of examples and so on. Okay. If you take, here's a nice thing to do, right? You have your batch algorithm, you're making incremental, and you get the same update. There's a good chance that you'll diverge. Okay, so you need to set it, separately. More questions? Okay, very good. So.